Cool. All right, so I have a few more minutes left, so I'll go ahead and go into the next part, which is the kernel trick. So the kernel trick basically is essentially the same thing like talking about support vector machines. You'll notice that with support vector machines, like this classifier, you see like all these other parameters right here, which are basically all related to the kernel trick. And basically, it's a way for us to cheat the system. Basically, we use a flaw called the curse of dimensionality, where basically when things are in higher dimensions, you tend to have more separability. And what that really means is that when we extend things out in higher dimensions, we have more freedom to play around with where we draw those lines. Okay, so the curriculum actually does like really great, what's it called, plot of this, but I'm going to say it in words a little bit, is that you can kind of consider, like, imagine like a line. I'm going to draw really quickly on here. If I were to draw our data point, so imagine like in 1 dimensions, and then we have something like this red dot right here. Okay, this red dot right here, another red dot right here, and we had something like a blue dot right here. Okay, and let's say this is like x equals 0. So x equals 0, and then this is like negative. So let's say this is like -1, -2. And this is like +1, +2. So it's like on 1 dimension, right? Well, if you look at this, right, if I get rid of those numbers real quick, okay, can you separate this with a single line? Probably not, right? Like if I drew a line right here, that wouldn't work, okay? If I drew a line right here, that wouldn't work, right? Basically, any single line I drew, I could never separate these 2 points are. So I'm done, right? I can't solve this problem. Well, what's kind of cool is that the kernel trick basically says, well, let's like raise all the red points up, for example. We'll just raise all the red points up and all the blue points down, and then we can just draw a straight line through it. So what this would look like is something like if I had a bunch of red points, with the goal, I would draw this like up here, and I'm motivating this a little bit up here, and then like a red point right here, okay? And then the blue point, we'll just keep the blue point, we'll keep the blue point right here. We won't move it. So you can see it's like, oh, if I had that then, if I had another direction to go, I could just draw a line right through here, right? And once I had that line right through there, boom, right? They're separable. Of course, I'm not using 2 dimensions. I have to still work in 1 dimension because there isn't another direction, but I can make one happen. And this is essentially what I do here. It's like, well, imagine this is x. I can use something like a parabola, like a parabola is going to be awful, by the way, but like you can imagine like if I drew a parabola like this, basically squared each part, right? You can imagine that it's like, oh, well, at x equals 0, it'll be at 0. At x equals like 1 or -1, it'll be like at y1 and y2 or y4, right? And you can go through and then do this part. And then what's cool is that I can take this point right here and this point, and I can actually draw, basically push this back down, and I can say, okay, these 2 lines by themselves are actually separating it directly. And what's cool is that I can still use the hyperplane or a line essentially to define this here in higher dimensions, and then say, okay, I'm going to lower it back down. Basically, I'm making fake features. I'm making a fake feature by using x squared as one of the features. So essentially what's happening is that this is what the kernel trick is. You basically split the data into new parts that didn't actually exist beforehand. Okay, and this allows us to use a separator in that higher dimension, because usually in higher dimensions, it's easier to separate things. And then we drop it back down low and drop it into a lower dimension from the original and use that crossover point with that kernel function right here to actually get this part. So it's as if we just said, oh, we'll just split it right here. Where in reality, we actually use essentially as a new feature x and x squared. So you can kind of imagine, like I drew this right here. If I had something like 2D data, I'm gonna use a color that's not yellow. I don't like yellow too much. It's a little harder to see. So you can see here is that if we had 2D data, okay, which is basically xy, right? What we can do is say xy, it's like, well, now we have a new set of features. So normally, like if I had a bunch of features like, you know, x and xy, for example, if I had just, this is x and this is y, and I drew out the data points, I'll just draw this a little bit with like orange. So you can see here, like maybe I have a data points like this. There's no single line I can do to actually figure out, oops, come on, there we go, Victor. All right. There's no way I can separate these out with a single line, right? But what I could do is say, well, let me put in a new feature. Let me also put in the feature, like if you imagine this in like your data frame, you might have feature X, feature Y. And then what we also have is like, okay, we'll also have X squared and XY. Or yeah, XY. And then we also have like Y squared. And essentially we have more features, more things to play around with, and allows us to say, well, okay, if we can't separate it just with XY, maybe we can separate it out with XY, and X squared. And then also we can draw a straight line through it or a hyperplane through it. Okay. Does that make sense to you guys? Thumbs up for feeling good. Sideways, you're like, thumbs down, feel good. Sideways, yeah. This is where I think the curriculum shows, like, honestly, visuals work really well. But the main idea here is that we're able to raise into higher dimensions and actually perform like that cross through it. So I'm actually just going to pull up the one from the curriculum from machine learning from support vector machines. Here it is. Kernel Trick. And I'm just going to pull up the GitHub so that's quicker to load. Okay, so you can see here is that this is our data with our X, Y, and essentially it's like, okay, well, let's just go ahead and square all those values and call that Z. So this Z might be, for example, X times Y, or, you know, it might be X squared or something. And then you can imagine now it's like all these points in the Y plane, or all these red points down here, those are going to be lower down. We can now make a hyperplane through that and actually make a new separation between those two. Essentially, we're making new features out of the original features we had. And that allows us to do that separation. And that's called the kernel trick. Okay. It's a little trippy, but hopefully that kind of makes sense. Of like, essentially, I like to think of it as like, we're just making new features. And once we have new features, it's easy to separate these things out. Yeah, hopefully that kind of makes sense a little bit. And note that this right here, using X and Y, we can use polynomial kernel. We can also do other options. And this is where if you look at SVC, you'll see that if you see kernel, you see that they have linear kernels, poly meaning polynomial kernels, RBF, which we'll talk about, sigmoid, which the curriculum talks about. RBF tends to be one of the most powerful ones because we'll kind of explain that a little bit. Basically, it's a special function that allows us to make more more divisions and stuff like going through. Okay, but note that this would be closer to like a polynomial kernel right here. But by default, we use something called an RBF kernel. So, sorry, RBF. So a radius, this should be basis function. So RBF is kind of like the common one. And basically, you say, okay, instead of just saying, well, let me just get X, Y, and X squared, we essentially make a new function that's going to split this up. So I'm just going to kind of walk through parts of this a little relatively quickly. But basically, imagine if you had like two different points, this blue point and this red point on this x-axis. We can draw like this line like centered around this blue point and this part right here. We can actually create this function called the RBF function, the radius basis function, and basically create this function that goes around here, centered around this blue or red point. And then what we can do, we can combine those functions together and basically say, okay, there's this one big function right here. And that's essentially what RBF is doing. RBF is actually this radial basis right here, this single function, and we combine them together because it turns out they're actually really easy to combine to make one big super function that describes a system. So if you imagine if you had like something like 5 data points, okay, like this, or sorry, if I actually have 2 data points, you can kind of see is that your function might look like this, but you can see here is that we actually have this blue and this red going forward. Sorry, I don't know if you guys can hear my dog kind of whining over there. But basically, this allows us there. And the big cool part about this is that we can say, well, all the red points, just make those negative. So what's kind of cool is if we had multiple functions like points like this, and I'm going to go ahead and draw this on here, instead of having just a simple radial function that kind of like, you can see a little bump right here. Like I'm just kind of making this up. This is not how it actually would look like, right? And then you might have something that's a little higher up here and then tapers off. What's cool is like instead of just having a simple function like this, we can actually multiply it by these negatives and positives. And so we can say, well, the blue ones are just say multiply that function by a positive and then have that red part flip down and actually would go down like this and then something like that. And that would actually create a nice basis function because now this red point would land right here. So if I actually did this in the right colors, but if I had this red point right here, these red points right here, and then essentially we can separate that, and I'm gonna use my green because I don't want to use yellow. We can separate this out, and now we have all the blue points above, all the red points above, below, and we can actually we can define this function very easily and say, once we have that part, we know where it crosses over, and essentially we can define where these points go through. Know that this works even with having the different data points non-separable, just like before. So what would happen here, what this would look like, is actually these data points would kind of, oops, this is my image tool. It basically would kind of go like this, and then would kind of dip down a little bit, and then go like this, and then like dip something like this. And we can still draw a line through here and say those are everything below that line is red, all the thing above is blue, and then just basically remap this onto our two-dimensional or one-dimensional or lower dimensional set. So radial basis functions are commonly used. That's why they're the default in sklearn. So hopefully that kind of like makes sense to you guys in the sense that we're just basically defining a function that's easy to make and just say, okay, all the points that are this color go up, all the colors that are this color go down, and essentially that we can separate those parts. This leads us, does that kind of make sense to you guys? Like in the concept at least of like making that function going through? Some kind of nods a little bit, like maybe not. This is where I think like it's the hard part. It's like, okay, well, why are we doing like a higher dimension? And basically it's like, we're just making a new feature. Again, that's kind of like the key part and everything like that. Okay, you dogs are so just they're coming at me like, hey, pay attention to us. So this last part though, this hyperparameter, basically this gamma allows us to say, do we want to have smaller circles or bigger circles? Basically, how steep do we want those radial basis functions? And this will allow us to be overfitting or lower underfitting. Hey. So we can, if for example, I just kind of quickly, this is exact code from sklearn. But if I go ahead, oops, I didn't run this part. If I go ahead and just look at an example from here, you'll see that basically, if I open this image, nope. Okay. You can see here basically our different gammas and our different C values. And you can see here basically is that these little like bulges going out like this, those bulges going out like that are actually, you can think of them as like little peaks and stuff sticking out in 3 dimensions. So I have a quick picture of this that can maybe help show a little bit. Here you go. So you can imagine like this is our original data here. And essentially we're using a radial basis function to either raise it up or lower it. So what would happen is that you have like this cross section going through, and that cross section is showing you essentially where the boundary is, which is what this looks like. You can kind of see almost like right here, that's kind of the boundary. You can see the darker blue is, you can imagine like either low valleys or, you know, the red and like high, you know, what's it called? High hills or something like that, high peaks. And you can see as we adjust gamma to larger and larger values. So you can see here, this is like 0.1, this is 0 or 1, and this is 10. You can see basically how steep or how narrow those peaks are and crossing it through. So this would actually allow you to say, well, this is overfitting. This is probably underfitting. This is probably just about right. And you can see here for the C value going on here is, do we care more about the boundary or do we care more about the classification? So you can see here is that for a lower C value, which are these ones up here, you care more about the classification of where, if they're crossing over or not, versus on these lower C values right here, we actually care about that boundary. I'm sorry, these higher C values, I mixed these up. This is where we care less about the classification, more about the margin. And here we care about more actually defining each individual part. So you can see here is that our boundary is well defined here versus getting a little fuzzy. And then over here, it doesn't have a well defined boundary. So these are hyperparameters that you would tune stuff to in the grid search to find the proper parameters. Okay. Anyway, I think this is more like something you can kind of play around with. If I had, let's see if I do this right. If I run matplotlib, I think you have it here. Did it plot out? No. Okay. Well, anyway, oh, I think I know why now. I didn't have the matplotlib in there, but it would produce that same graph in there. There it goes. So you can see here the similar kind of same thing. So you can basically use a grid search and kind of see different parameters, which one works well for you. And that's the kind of kernel trick, kind of like how you would use that for parameters. I know I kind of went through that relatively quickly, but hopefully that gives you like an idea, like visually what's going on. And I suggest, you know, going through like, as the more you kind of go through it, the more you kind of like think about it, I think it kind of helps visualize it. But are there any questions you guys have? No? Sound pretty good? Okay. Sideways, you're like, yeah, whatever. I can let you guys go. I know it's getting a little later in the day. Yeah. Okay, I'll go ahead and stop it here then.